All right, so this is a quintic. That is a 5th degree polynomial. Now, I didn't write it out in the form, the standard form I gave you of a polynomial, which a 5th degree polynomial I would write as ax to the 5th plus bx to the 4th plus cx cubed plus dx squared plus ex plus f, right? So I didn't write it like that. So how do I know that it's a 5th degree? How do I know that the highest power of x would be a 5? There's 5 factors. Yeah, there's 5 factors here. So if I multiply them all together, without having to actually do the entire multiplication, which would take forever, I can tell what would happen because each of them has an x. When I multiply all those x's together, I'm going to get my first term would be x to the 5th. And then the rest of it, you know, would take forever to figure out. But I do know that first term would have to be x to the 5th. So I know it's a 5th degree polynomial, which we call a quintic. And when you write it out in factored form like that, it makes it really handy to be able to answer certain kinds of questions. Like, what are the solutions to this equation? If I take that polynomial and set it equal to 0 and try to solve for x, when it's all factored like that, how would I go about solving it? Yep. So you would set each factor to 0. So I'm multiplying a bunch of things together, and the answer is 0. That means at least one of those factors has to be 0 to get an answer of 0. So x minus 5 is 0, or x minus 10 is 0, or x plus 7 is 0. And so my solutions are going to be x equals 5, 10, 2, -3, and -7. If I put any of those values in for x, the equation will be true. The polynomial will equal 0. Okay, so question B asks, what are the zeros of p of x? So that's just a synonymous way of saying, where does that function equal 0? So question B is exactly the same as solving this equation. Okay, so this is a synonym. This means, where does p of x equal 0? To find the zeros, that you set it equal to 0. So my solutions are the same. X equals 5, 10, 2, -3, -7. Now, what question that we're sometimes asked uses the procedure of making y 0 when solving? What question are we usually answering when we do that? We're talking about the graph of a function. Finding the x-intercepts. Yep. So setting the equation equal to 0, finding the zeros of the polynomial, and finding the x-intercepts of the polynomial are all the same question. Okay, so I can ask that same question 3 different ways now. And the word 0 we haven't formally used before, but it is the command that we've used in the graphing calculator when we were looking for x-intercepts. So if you go in here, when we were looking for x-intercepts, we'd go into the calculate menu and choose option 2, 0. That's how we found where we crossed the x-axis. So they were using this term 0 to mean x-intercept long before we actually introduced the term. But now we've officially declared the word 0 means where the function equals 0, which is also where you find the x-intercepts of the graph. Okay, and then finally, just taking a look at this graph, how many extrema does it have? 4. for local maxes and mins combined. All right, so that about finishes up class 28. We're going to skip this activity. You can look at it later on your own if you want. And we're just going to jump to class 29. Okay, so class 29 is about polynomial modeling and polynomial regression. So it's chapter 2 and chapter 3. At the end of each chapter, there's a little section that says focus. So those are the sections that we're working on. So in chapter 3 focus, we have a variety of examples where we're asked to find models that can be constructed using geometric or algebraic properties of the particular situation we're looking at. So we're asked to find functions that model volume, area, surface area. So here's a typical problem. We have 20 meters in fence to enclose a rectangular pen along an existing wall. Find a function that models the pen in terms of the length of the side opposite the existing wall, and then find the dimensions of the pen and maximum area. Okay, so we did a problem similar to this, maybe Monday? I don't know, one day. So we have an existing wall, right? I'll draw this like in red to represent the existing wall of a building. It's supposed to be like bricks. And then I'm going to build a pen against that wall. So I've got a rectangular pen to build against that wall. And I have 20 meters of fencing. So these two lengths have to be the same because it's a rectangle. So if I use x on each side, how much do I have left to connect them? 20 minus 2x, because I have a total of 20, and I've already used 2x. So a function that models the area as a function of x. Actually, they told me that x is supposed to represent the length of the side opposite the existing wall. I should have finished reading the question. If we let x equal the length of the side opposite the existing wall, what do those two equal pieces have to be? (20 minus x divided by 2). So I have 20 total, subtract the x I already used, divide it in half because I have to use half of it for each side. All right, so then my area of the pen as a function of x would be length times width. X times 20 minus x over 2. And if I were to multiply this out, I would get negative 1/2 x squared plus 10x. So I distributed the x, then I divided the 2 into both terms, and I changed the order of the addition. Okay, so there's the first part of the question. That's the part that they asked me to find a model, find a function that models it. Find a function that models the area. So we got that. And then we're supposed to use that function to find the dimensions of the pen of maximum area. So this area function is a quadratic that opens down, right? So if I find its maximum, then I found the maximum area. So I want to find the vertex. How do you find the x-coordinate of the vertex of a quadratic? Somebody's got to remember, we just talked about it Monday. Negative b over 2a. So I get negative 10 over 2 times negative 1/2, which is 10 over 1, which is 10. So that's my x. That's the x coordinate of the vertex. So that's x has to be 10, which means that the height of my pen, or the width, would be 20 minus 10 is 10 over 2 is 5. So a 5-foot by 10-foot pen is the best I can do. That's the maximum area I can make. And what is the maximum area? 50 square feet. Right, just multiply the 5 by the 10. Okay, so that's sort of a typical modeling problem. Okay, another one might be the box problem that we just skipped. So I'll give you a couple minutes to do that later, but the waste-free box would be another typical one. Actually, let's just do the beginning of it together. So let's say you have a standard sheet of 8.5 by 11 typing or notebook paper. We can transform it into a box. We can make it into a box if we cut squares out of the corners. So I have a piece of paper, and from each corner, I'm just going to tear out a little square of equal size. This obviously could be done neater, more accurately. So I tear out a little square from each corner, and then if I fold up each of these little notches that I've created, and kind of like tape them together, it makes a box. Okay. All right, so the question is, how big a square should I cut out of each corner to maximize the volume of the box, to make the biggest box possible? Okay, so I want to first express the volume of the box as a function of x, and x is going to be the side length of the squares we cut out. Okay, so I'm cutting out these squares that are length x. Okay, and once I fold it up, what is in general, the volume of a box is length times width times height. What is its length, the distance along the base of the longer side? 11 minus 2x, yeah, because the whole length of the paper is 11, and then you cut an x out of either side, and that becomes the base, 11 minus 2x. And then the width is this distance here, right? It was 8.5, and you subtract an x off of each end, so you get 8.5 minus 2x. And then what's the height of the box? X. Good. So there's a formula. There's my function for volume as a function of x. So v of x is 11 minus 2x, 8.5 minus 2x times x. So then what's the domain of v? What values of x make sense to plug into that function? Like, what's the smallest x that makes sense given the physical constraints of this problem? 1? Or something bigger than 0, yeah. So I think that's probably why you were thinking 1. But you could also do like a 1/2 inch, something smaller. Yeah, so something bigger than 0. Okay. And what's the largest x that makes sense for this problem? Yeah, it'd have to be less than 4.25, because if you went more than 4.25, well, if you went exactly 4.25, you're just going to cut the paper in half, and you're not going to be able to make a box. So it has to be less than 4.25. So I put a round bracket. I mean, really, 4.24 would be really tough to make a box because you just have like a little teeny. it's a theoretical box. All right, so now I want to draw a graph of the function v. So I'll just use my graphing calculator to do that. Oops, oh, I hate when I do that. Okay, so I can't actually, this isn't a quadratic, right? When I look at my formula, 11 minus 2x times 8.5 minus 2x times x, what's the degree of that polynomial? If you multiplied it all out, what would the highest power on x be? It would be a cubic. Yeah, because I've got an x in every term. When I multiply them together, I'm going to get an x cubed. So this is a cubic, which means I can't use the negative b over 2a trick to find the maximum. There really isn't a trick. So I have to rely on my calculator to estimate it for me. So go to your calculator and you go calculate maximum, and you give a left bound and a right bound and a guess. And it looks like x is 1.58, y is 66.14. 1.5, 1.59, 66.15. Yeah, okay, so those are the coordinates of my maximum. So what is the maximum area of a box that I build this way? What's the biggest area that I can, or volume that I can make? 66.15 cubic inches. All right, so that's enough. We don't have to go through the whole rest of it. But that's the general idea of the first part of today's lesson. Using something geometric to write a, or something in real life, to write a formula for a function that models it. Whether it's a rectangular garden or a box made of paper. Okay, so now we're going to move on to regression. Earlier this semester, we entered data into our calculators and did linear regression, and you did a project on it. Now we're going to see what to do if the data is not very linear. Okay, if the points don't fall in a nice line. We can actually use a polynomial to model the data, because polynomials have ups and downs and mins and maxes, so they can model data better than a line in some cases. So here's an example. We have a table that shows the number of women in the full-time civilian labor force in some selected years. And I'm going to do a linear and a quadratic regression and compare them. So first we got to enter the data. So we got to do a little review about how to do that. So you press Stat. Option 1 is Edit. Go in there. If there's any data in there, you want to clear it. So you highlight the name of the list and press Clear. That will take the data out. And then I think I'll measure in years since 1900. So 1910 would be 10 years since 1900. And it doesn't say what to do, so you can choose whatever you want. You do have to be careful in WebAssign that sometimes they tell you how to enter the data, and you have to do it that way or you might get the problem wrong. All right, so I've got 1910, 1930, which is 30 years after 1900, 50, 70, 90, and 100 years. And then we have, this is measured in millions. So 7.4, 10.8, 18.6, 31.5, 56.8, 67.5. So one quick little check you can do to see if you made any typos is to make sure your two lists are the same length. Just a quick double check before you move on. All right, so now what I'd like to do is I want to find the line of best fit and a parabola of best fit. So first, let's just look at the data. We're just going to look at the scatter plot. So if you go to y equals, clear what's in there. We don't want to look at any old stuff. And put the cursor on plot 1 and hit enter so that it's now highlighted. That means it's going to plot your data that's in list 1 and list 2. All right, and then I have to choose, I can either choose a window or have the calculator choose a good window. If you do zoom 9, it chooses a perfect window for your data. So it actually doesn't look like a line would be too bad a fit, but it does have a little bit of a curve to it. So I'm gonna do both a line and a curve fit and see which one's better. So in the calculate menu, oops, no, not that one. Go into the stat button and in that calculate menu, choose linreg, and we're going to do L1, comma L2, comma Y1, which you found under the variables key, vars, yvars, function Y1. So I'm going to have it do a linear regression, paste the results into Y1. So this is all stuff that we've done before. And I get an R value of 0.956, which is actually really good, right? That's really close to 1. So my line is a pretty decent fit. And my equation is y equals 0.68x minus 7.8 r squared, which we usually look at r, but I'm going to look at r squared because when you do polynomial regressions, they only give you r squareds. They don't give you r's. So we're going to just look at the r squareds to compare. They are related exactly as you think. If I take the square root of that, I get r. If you take the r value and square it, you get r squared. All right, so that is a really good fitting line. If I look at it, graph, my points are all like pretty well clustered around the line. Looks pretty good. But I'm going to do the regression again, but this time instead of a linreg, I'm going to do quadratic, which is going to fit a parabola to my points. So you go stat, calc, and this time do option 5. The one under linreg says quadratic. And you do the exact same thing. List 1, comma, list 2, comma, vars, yvars, function. And this time I'm going to use y2. I'm going to put the results in y2 because I already have something in y1 and I want to keep it there. So I'm just going to put the results in y2. And this time, vars, yvars, function, and then choose y2. So this time it spits out a function that's quadratic. It has the form ax squared plus bx plus c, the basic form of a quadratic. And we have 0.008x squared minus 0.23x plus 9.4. And my r squared value is 0.997. Really close to 1. So which of these would you feel more comfortable using to make a prediction? the quadratic, fit our R² value. And if I look at the graph, so there's my linear regression, and here's my quadratic fit. So almost perfect. So it's almost a near perfect fit. So if I want to make a prediction, so we'll call this one Y1 and this one Y2, because that's where I pasted them. I want to make a prediction for the number of women who are working this year. What should I plug in for X? $113. Because I was letting 1900 be year 0. So 2013 would be year 113. So rather than typing this in, because I rounded all these values, this 0.008 and 0.23 and 9.4, those are all severely rounded. I cut off a ton of decimals. So rather than just go to my home screen and type it in, I'm going to use the table. Plus, that keeps me from making typos. So go to my table, and I want to type in 113 for X, and it gives me a value for Y1 and for Y2. Okay, so Y1 predicts 69.5 million women, and Y2 predicts 87.9 million women. And we're going to use Y2 because it seems like a better fit. How confident are we in the accuracy of this? Do you think that? Pretty confident. It's a good R² value, and it seems like that trend would continue. That trend makes sense that it's going to be increasing, right?
Were we using R value?
We were using R for linear, and now we're using R² because it's just a quirk of your technology that when you do a polynomial regression, it doesn't give you R, it gives you R².
Oh,
yeah. So for linear, you get both, but for anything higher than linear, you just get R².
but
It gives you both. Yeah.
I missed that.
Right, sorry. Pretty confident because that pattern of growth makes sense to us, right? It does seem like the number of women in the workforce will be increasing. And the last piece of data in the data set was the year 2000. 2013 is not that far outside the data set. So even though it can't increase forever without bound, right? We're not someday going to have, you know, a gajillion women in the workforce. But 13 years outside the data set, it seems that that trend, it's safe to assume that that trend would continue for a little while. All right, so our 4-step modeling process. First, you make a scatter plot. Just put your data in your calculator, make a scatter plot, and decide whether a line or a parabola or a higher degree polynomial curve should fit the points. So the more peaks and valleys the data has, the higher the degree of your polynomial should be, right? 1 valley or 1 peak, quadratic's a good idea. 2, use a cubic, right? Because we had that theorem last class that said a polynomial of degree n can have at most n-1 turning points. So a 4th degree polynomial could have 3 turning points. So if you have 3 turning points in your data, you need a 4th degree polynomial. Does that make sense? No? Okay.
I don't understand how that.
Yeah. So imagine, not yet, but we were going to. Imagine your data looks like this. I have to decide what degree polynomial to use to model it. Well, I know to get 2 extrema, I can't use a quadratic, right? Because the most extrema a quadratic can have is 1. 1 less than the degree. So the smallest degree I could use is a cubic, because a cubic can have at most 2 extrema. So if you have 2 peaks and valleys, 2 extrema, the smallest degree you can use that will capture that behavior would be a cubic. Does that make sense? So we're going to start using not just linear and not just quadratic, but cubic and quartic and quintic. Okay, so you can use whatever degree polynomial you want, and the degree you choose depends on the behavior of the data. 1 peak or valley, a quadratic makes sense. 2, use a cubic. 3, use a quartic, etc. All right, so then you have your calculator find an equation for your model. When you go into the calculate menu of your calculator, the stat calculate menu, we have linreg, quadreg, cubic reg, and quartic reg. So you can go up to a 4th degree. Verify that your equation has a graph that comes close to the point. So look at your equation graphed with the scatter plot. And if it doesn't, you either need to pick a new kind of regression or check for mistakes. And then you can use your equation of the model to draw conclusions, make estimates, make predictions. Okay, so why don't you try the first few of these? We'll spend, 20 minutes or so working through this activity about polynomial regression. And I will come around and help.